P.3 radicals and rational exponents. We're going to start off with square roots, and a square root is saying when one number is multiplied by the same factor twice, then its square root is that factor that you are multiplying by. Okay, so that's what we're looking at there. Some vocab just to remind us there. We have this radical sign, that's this symbol here. Remember that that is the implied 2. If there's no number there, it's implied that it's a square root or the 2 root. And as we go through some of these, we're going to see cubed roots or to the 4th root and such. But if there's no symbol, it's implied it's a 2. And that says you're looking for something inside that when it's multiplied by itself twice, so there's 2 of them, then you can factor or pull that out of the radical sign. The radicand is whatever values are inside underneath the radical sign, and the entire thing is called a radical expression. Now, if you're used to me, you know, sometimes I call it square root, sometimes I call it radical. The words kind of interchange for me when I say it. But if I ever confuse you and you're not sure, come back to this and think, well, the radical just means something under a root sign of some type. Okay, so let's just start. Evaluate. Remember, evaluate is what we do instead of solve because we don't have an equal sign, so we're simplifying as much as possible. The square root of 121. So you're asking yourself, what number times itself will give me 121? Because I need 2 of them to pull out of a square root. So some of you might say 11, and some of you might say negative 11. So there are actually 2 answers here, positive or negative 11. Okay. On number 2 here, I have negative the square root of 1 over 16. Remember, when you have a fraction inside of a square root, you can separate it, square root of 1 over the square root of 16. And that number, that negative can hang out front there. Square root of 1 is 1, square root of 16 is 4, and the negative out front will there. Just a quick reminder, I'm not going to make you do the plus or minus on all of them. The plus is fine if it there, and then if they really want the negative, they're going to show you that negative. So that's kind of how we'll use our rule of thumb. But always remember there's 2. We will get farther into pre-calc where we're going to need to remember that there are 2 roots, and that will affect answers later on. For number 3, the square root of negative 25. There are no 2 numbers that are real numbers when multiplied times self will give us negative 25. So for this reason, there's no real root. Okay? And you'll notice I wrote no real root. I didn't say no solution. I said no real root because technically there is a solution when we get into the complex world. Okay, so just keep it in mind, no real root or no real solution right now. Number 4 is going to stress to us the rule that I went over with you the other day when we were doing order of operations. And remember, a square root sign and things underneath it, that's kind of an invisible parenthesis there. So technically it would have this like 36 plus 64. So if you have more than one thing going on underneath that radical sign, you need to make sure you simplify as much as first before you try to take the root. So 36 plus 64 is 100, and I can say the square root of 100 is 10. And again, we'll just stick with the positive value, keeping in mind that there is a negative value as well. All right, so a couple rules that they're going over here for us. And this first rule is going to kind of reinforce what I just told you. For any real number a, if you're taking the square root, let's stick to the absolute value, which means I'm going to give the positive value, okay? And again, if they want you to make sure you use that negative value for what we're doing today, they're going to throw a negative out front. So you're going to be able to remember to give that negative value, okay? Now, the product rule for square roots is just a reminder that you can basically multiply together or separate the factors. It's your choice. So if you have 2 factors already underneath there being multiplied, you can separate them into 2 separate ones, which means maybe one simplifies and one doesn't. Or if they are separated, you can join them underneath here. And the rule is you can multiply anything. If radicals are being multiplied, you can multiply what's inside together, whether they're the same or whether they're different. It doesn't matter. The same thing goes for the quotient rule. We used it up there with the square root of 1 over 16, that if you have a fraction under a square root, you can separate it into 2 separate top and bottom, numerator and denominator, in the roots. Or if the roots are separated, you can make it 1. And the best thing for this is sometimes there is some simplifying that can get done, and that will help make the radical a lot easier to work with. All right, so let's try a couple here. I have number 5. I have the square root of negative 13 squared. And of course, on my screen right now, you can't see it, but if you remember the earlier rule, it says whatever is squared, the square root and square, remember they kind of cancel each other, your answer is going to be the absolute value of what's in there, which means the answer for this is 13. Okay, it is not negative 13. Now, I'm going to do it kind of a slightly separate way so you can see it as well. If I followed order of operations here, inside I see a power. So if I take negative 13 squared, I would get the square root of 169. And then when I take the square root of that, I would get 13, which reinforces that idea that if something is squared inside, its absolute value, always positive, will be the answer. All right, on number 6, we have a product rule going here. I see two separate radicals, and they have different things underneath, but it doesn't matter. I can actually just multiply them together and join what's there and go from there. Quick side note, because this example doesn't show it, if there are values outside of the radicals, remember outside values multiply together, inside values multiply together, and then you simplify from there. This one only has inside, so I'm going to go ahead and multiply these together. 2 times 10 is 20. Y times y is y squared, not 2y. Don't let your algebra get a little bit, what was I going to say there? See, I can't even speak because it's been so long. So, yeah, anyways, I'll finish that thought some other time when the word comes to me. So I get the square root of 20y squared. It's time now to do some simplifying. So I look at 20 and I say, does 20 have any factors that repeat, right? So, or if you think about it, or does it have a factor that's a perfect square? In my classroom, we often call them the pretties. Is there a pretty in 20? Yes, there is. 4 times 5. And remember, I'm looking for pairs. So what pair is inside here that I can pull out? Well, the square root of 4 is a pair of 2's, so I can pull out 2. The square root of y squared, there are 2 y's. I can pull out a set of y. And I'm left with just 5 underneath. So 2y square root of 5 for my simplified answer there. Number 7 is going to use our quotient rule, which says if you have separate square roots in a fraction, you can join them together in one big division problem. And that's how we have to think about it, not a fraction, but a division problem. So I can put 500 x cubed on top, 10x to the negative 1 on the bottom. And now I need to think of it this way. I said it was one, division problem or fraction. I'm going to think of it now as a fraction or division problem. Can I reduce that fraction first? Well, 500 divided by 10 is 50. And our power rules that we went over the other day, if I have an x to the third on top minus, and I subtract the power on the bottom minus that negative 1, I get x to the fourth. And notice I have no more fraction, no more division anymore. It's just square root of 50 times x to the fourth. I'm looking for pretties or a pair of factors that are the same. 50 is 25 times 2. And so the square root of 25, or the set of factors that make 25, is 5. 2 does not have a set, so it stays inside. And x to the fourth, there are 2 pairs of x squared, so I can pull out x squared. Okay. Questions so far? Good, because I couldn't hear you to answer them anyways. But I'm sure if you have one, you're going to send me a note and send me an email, right? All right. Talking about adding and subtracting square roots. I don't remember if you remember one of those first couple days in geometry when I went through my radical world notes, because I told you it's a crazy world. And remember, when we add or subtract square roots or any type of roots, the only way you can join by adding and subtracting is if you have the same radicals or values of those radicands, okay? I also said kind of you can only play with your neighbors if you are the same kind of ugly, because we call what can't come out of those radical signs the uglies, and we leave them inside. So if we can't get the same number underneath the radicand or underneath the radical sign, we cannot add or subtract the outside values. So always simplify first is what we need to do here. Square root of 18, I'm thinking 9 times 2. So I already have a 3 on the outside. So that 3 stays. The square root of 9 is 3. When it comes outside, don't forget those multiply together when they come outside, and we leave the ugly 2 inside. Square root of 50 is 25 times 2. I already had that 5 outside. When I take the square root of 25, I get another 5, and it multiplies by what's out there, and I leave the ugly square root of 2. That gives me 9 square root of 2 plus 25 square root of 2. Now that I have my values actually simplified as far down as they can, I can look and say, do they share the same radicand? And because they do, I can join them, but remember, I only join the outside values. That radicand is like their last name now. It doesn't go anywhere, it doesn't change, it just stays there, it's hooked on there, you don't change the value. So I only add the outside values. 9 plus 25 is 34, and I leave the square root of 2, and there's my simplified answer. More of them on number 9, so we have a little work to do here. Looking for perfect squares in 54. Okay, I think I can do 9 times 6. In 24, I think I can do 4 times 6. In 96, this is where I really wish we were in class together because I would make you come up with these numbers for me. 16 times 6. And finally, 63, I believe, is 9 times 7. Okay, so we break them all down. Now we're going to pull out and simplify. Square root of 9 is 3. When I multiply it by the 3 on the outside, I get 9. Notice I'm skipping some work here. Hopefully you're following. Square root of 4 is 2 times the 2 on the outside is 4. Square root of 16 is 4. Square root of 9 is 3 times the 4 on the outside is 12. And now I have my simplified values. When I look at this, remember, you can only join those who have the same radicand, and it looks like I have 3 of them that share that same radicand, so I'm combining just their outside values with the operation shown. 9 minus 4 is 5, minus 4 is 1, so I get 1 square root of 6. This 12 square root of 7 is that oddball neighbor that does not have the same last name, cannot join, and he just has to look and watch the rest of them play together. Remember, on the square root of 6 over here, you can have the 1, you can skip it. There's always that invisible 1 if it's not there, so it's up to you whether you want to have that or not. All right, feeling good so far. Hopefully this is all review. All right, moving on to the second page. Look, I remembered to go to the top of the page before I started my notes this time. I'm learning. I'm not so rusty. That's the word I was looking for here earlier, rusty. Don't get rusty in your algebra skills. Okay. Anyways, back to this. We are talking about, we kind of did the addition, we did the subtraction, those two use the same rule, and we talked about the multiplying, simplifying the division, we talked about that. But remember, technically, you cannot have a radical in the denominator ever. And to get rid of that, we call that rationalizing. Okay, so if I say rationalize the denominator, it means you need to make that pretty. It cannot keep that square root in there anymore. So we have two processes. If you just have one value on number 10 underneath the in the denominator, we just need to somehow make that a perfect square root so that we can turn it into an integer and no longer a radical. So the easiest way to do that is to multiply the numerator and the denominator by the smallest number that will produce a perfect square root. And to be honest, it says smallest number. Sometimes there are numbers smaller, but I'm going to be honest, multiply by one that just makes sense to you, and we'll do the simplifying at the end if we need to. So for me, I see the square root of 10. Well, if I want to make that a perfect square, why not make it square root of 100? Because 10 is easy to get to 100. So almost always the rule of thumb is multiply it by itself, the square root of 10. And what I do to the denominator, I have to do to the numerator because I can't really change a value. And when I look at that, I'm technically multiplying by 1, and multiplying by 1 does not change anybody's value. And so I can do that on top and bottom. So across the top, I get 2 square root of 10. Outside numbers multiply, inside numbers multiply. Those two cannot go together because one's outside and one's inside. In the denominator, I get the square root of 10 times the square root of 10, which is the square root of 100, which is what my goal was, and many of you will skip that step and simply write the 10 on the bottom. And that's fine. Take the square root of 100 and you get 10. Remember, I tend to overshow sometimes in notes, especially when I'm doing these videos, because I don't want to lose anybody in the process of what I'm doing. Number 10 is looking good, but we always need to stop at the end and say, is there any way I can reduce? And reducing this is just like when we multiply. You can reduce outside numbers, you can reduce inside numbers, but you can never reduce an inside with an outside. So I only look at my outside numbers right now, and the 2 and 10 there can both be divided by 2, and because of that, I'm going to get square root of 10 on top and 5 on the bottom. Notice on top I left my invisible 1. If you write that invisible 1, I have no problems with that, but I can get square root of 10 over 5. Okay, the second process, though, if you do not have just a single factor that's a radical in the denominator, is when you have an expression such as 3 plus the square root of 5. So this is where we go to this method called multiplying by conjugates, okay? And I want to remind you, you use conjugates in complex numbers when you are working with that imaginary I. There are other times we use this conjugate, but this is one of the largest times when we have an expression, meaning more than one term that cannot be joined in my denominator that involves a radical. So I need to multiply. Well, notice over here I multiplied by one thing. Well, 1 times 1, you multiply them together, you go from there and you simplify. But when I have a factors, two terms, if I want to multiply by something, when I multiply two things times two things, I'm suddenly needing to FOIL, okay? So when you start thinking about foiling, we've got 4 terms that come out of multiplying 2 terms times 2 terms. We want to make sure none of those 4 terms, by the time we are done simplifying, are still radicals. So when we multiply by the conjugate, we can try to get rid of those, and that's the pattern. So here's what we need to remember. When you multiply polynomials together, which, funny to say, we're going to do that in the next lesson, but it's also review, so you've had it before. There are one type of factors that basically the middle terms will cancel each other, and that's really what we're going for here. And a conjugate means you take your value of the first one and you use the same numerical values, okay, in your second one, but we're going to do the sign, change the signs up a little bit. So I get 3 and the square root of 5. But if I want my middle terms to disappear, I need to multiply by the opposite sign of what I see here. So I'm going to use 3 minus the square root of 5. Now, the same rule applies from what we did earlier. What I did to the bottom, I have to do to the top. So I'm going to multiply it by that 3 minus the square root of 5 on both the top and the bottom. Across the top, I have a little distributing to go. You know what? I'm going to do this on the bottom because I'm going to run out of space. So 6 times 3 is 18. 6 times the negative square root of 5. The 1's an outside number, 1's an inside number. I'm leaving it minus 6, the square root of 5. All right, in the denominator, remember I just warned you, we're multiplying a binomial times a binomial. Because of that, we need to FOIL, okay? So remember, FOIL, the first. That means the first in each one. 3 times 3 is 9. Outside. Those are my outside terms. My outside 3 and my outside negative square root of 5 gives me a negative 3 square root of 5. My inside terms when I'm foiling here. So that gives me positive square root of 5 times 3 is positive 3 square root of 5. And finally, the last terms when I FOIL. So I have the square root of 5 times negative square root of 5. And a positive and negative make negative. I can multiply those together and get the square root of 25. Okay. So on my numerator, I can't do anything right now. It's staying 18 minus 6 square root of 5. Those are not like terms. They're not going anywhere. Okay, in my denominator, what I see is great right here is negative 3 square root of 5 plus the square root of 5. That is the joy of multiplying by a conjugate, is you should always get those middle terms to cancel. Make sure you use opposite signs, so, or they won't cancel. All right, and don't forget the square root of 25 is 5. That is a minus in front of that to join with my 9 over here. 9 minus 5 is 4. Okay, it's looking much cleaner already. And just a quick reminder, you're always allowed to have radicals in the numerator, but you cannot have those scary monsters in your basement, so make sure you don't have them in the denominator. One last step, can I simplify? Now, once again, we're using those outside numbers and those inside number rules. There's only one thing on the inside, so that 5's going nowhere. So I have to look at all 3 of these together, and do all 3 of them have a common factor? If they don't, you're done. Don't worry about it. But if they all 3 can be divided by the same number, which in this case is 2, I can reduce. And 18 divided by 2 is 9. 6 divided by 2 is 3. But remember, it still has that 5 on there. And 4 divided by 2 is 2. So there's my most simplified answer. Okay, just a quick note. If you are having to look in the back of the book for answers, possibly they wrote this 9 over 2 minus 3 halves radical 5. Maybe you could technically, I guess, write 4.5 minus 3 square root of 5 or something. So just know that This is easiest to leave it in this format. Obviously, it can be written in a couple different forms. Okay. We're going to talk about more than just a square root, okay? This is talking about the nth root of a real number. So I kind of warned you earlier that if there's a square root, we just imply that I'm looking for pairs of two factors that make up something in the inside that I can pull out. So this n, also called the index, okay, up in that corner, can change. So if I have this cubed root, that means I'm looking for a factor that multiplied by itself 3 times creates a number inside, then I can pull that factor out. Of course, if I have something to the 4th root, I'm looking for a factor that's been multiplied 4 times to make a number, and then I pull out just that factor, okay? So on some of these, maybe the best thing to do is turn it back, a number back into factors to see if indeed you do have that, okay? If you know some of these numbers, that's fine. I'm going to warn you, sometimes the best thing to do is have a little chart maybe somewhere that, I don't want to say you have to memorize it, but the more you recognize those numbers, the easier these become. And if you make a chart and you're checking it every so often, those numbers will eventually just kind of pop up in your memory. Oh yeah, that one's that. Oh yeah, that one's that one. So when I'm saying a chart, I'm saying you might make a chart, and maybe I'll even give you one in class. I'll have to see if I can come up with one. You know that like 2 squared is 4, okay? So you might make on your chart, well, 2 cubed is 8. 2 to the 4th, that's times 1 more 2, that's 16, right? 2 to the 5th is 32, and so on. Okay, I could keep going here. And 2's, the 3's, the 4's. Now I'm going to tell you what, like you get to 4, and 4 to the 3rd is 64. Your numbers are getting big fast. If these numbers are anywhere underneath 100 that we're looking at, you're probably not much more than working with the 2's and the 3's, okay? So, but again, the more you recognize them, the easier this is. Okay, so I have on number 12, 81 to the 4th root. Now, a quick reminder, when you have even number roots, the square root, the 4th root, the 6th root, the 8th root, and so on, you can only take the roots of positive values because you have to have an even pair, and the only way you can have an even pair to pull out is if you have both the same sign, which is positive. If you have an odd root, the 3rd root, the 5th root, the 7th root, and so on, you can take out a negative factor, okay, because you can have an odd number of factors, which means you can, with an odd number, you get a negative value that still is in there. So just kind of keep that in mind. Even roots, all my answers should be positive. Odd roots, I could get a negative value. Okay, so on the first one, I have 81. Well, just a quick reminder, and again, this is something you can do if you need to. I could take 81 and I could start breaking it down. Well, 81 is 9 times 9, but that's not my smallest factor. Then I get 3 and 3 and 3 and 3. That's the smallest I can go. But notice what I have are 4 3's that would multiply together to go back to that 81. So just to kind of give you a visual here, I can kind of write it this way. 81 is the same as 3 to the 4th power. Well, a 4th power and the 4th root is saying what term to its 4th power would make this value? Well, that answer would be 3. Okay, so on the 4th root, I'm looking for that factor that multiplied by itself 4 times, gave me that larger value. Okay, negative 27. What times itself 3 times will give me 27? Well, that would be 3, but it's negative, so it would be negative 3. So I'm saying negative 3 times negative 3 times negative 3 makes negative 27. And remember, you can always replace things inside with a value it's equivalent to. So now I'm asking you, in the 3rd root, what number times itself 3 times gave me negative 27? Well, that would be negative 3. And remember, you can have negative answers on an odd root, but not on an even root. Okay. Now, 14 is showing us that even though we're working with a cubed root, the rules still apply. If I'm multiplying 2 together, whether they're the same or different, I'm allowed to multiply them. And so 9 times 6 is 54. And I can join this and make it one big cubed root of 54. Now, I can tell you right now there's no number that times itself 3 times is 54. But is there a factor of 54 that does this? And again, this is where the tree over here might be really helpful for 54. So on 54, I'm going to start, I know it's even, so 2 and 27. And then 27 could be 3 and 9. 9 could be 3 and 3. Doesn't look like I'm going to do any more there. Because I'm on a cubed root, I'm looking for a set of 3, and it looks like I have 3 3s, and then I still have that 2. I can't forget that 2 because it's still one of the factors that made up 54. I'm taking the cubed root. Cubed root of 3 cubed is obviously 3, so that can come out. But I cannot take the cubed root of 2, so in my radical world, I still call that an ugly. It's got to stay inside until it can find some more factors to join with. So that's it. 3, the cubed root of 2. It's so important to make sure that you put this little index right here, because if you leave it 3, the square root of 2, you have changed the value of the problem. So make sure when working with any radical that is not the square root that you leave its index there to remind people of what that is. All right, 15 is going to use that same rule from the quotient rule from the front page again, which says if you see two things in the same, and this is important, you have to make sure these indexes are the same. If one's a square root, one's a cubed root, you can't do it. But because they're both a fifth root, I can turn this into one big fraction. And I get 64x to the 6th over the 2x. And what that allows me to do is do some simplifying before I try to take the fifth root. Well, 64 divided by 2 is 32. X to the 6th divided by x is x to the 5th. And it's still to the fifth root. Is there a factor times itself 5 times that makes 32, or is it a factor of 32? And just a quick reminder, if you had a chart going or something, in fact, it's probably, oh, look, it's right there. 2 to the 5th is 32. And I'm taking the fifth root. So what factor times itself 5 times gave us a value in there? That would be 2. How many pairs, or no, I have to say this the right way. When I'm in the fifth root and I see a variable, I'm asking myself, how many sets of 5 can I pull out? Well, there's one set of 5, so I pull it out, and I have nothing remaining. So I don't need to write my final, any radical in the final. And 16, the last one here. Once again, adding and subtracting, it follows that rule that unless the exact same values are the radicands, you may not add or subtract the outside values. So we need to do everything we can to simplify first, and then check to see if we are allowed to add or subtract. So we are looking at the cubed root, so I'm looking for factors that are 3, right? So I'm going to think of, for 24, 24 is not a perfect cube, but 8 times 3, 8 is a perfect cube. So I can take the perfect cube of that is 2. That means my 3 is staying inside there. Are there a set of 3 x's? No. So that x stays inside. Are there a set of 3 y's? Yes. How many? Just 1. So we pull out 1 y, and we don't have to leave any inside. So we've simplified that first radical. Looking at the second one, I already have a, now be careful here, that x is not, or I'm sorry, that y is not y to the third, it's simply y. It's already out there, okay, so I'm going to leave it out there. And I'm looking for this cubed root. Well, the cubed root of 81. Well, remember over here on the left, we had 4 3's, okay? So if you think about this, if I write 3 to the 4th power x, right, and I'm taking the cubed root, how many sets of 3 can I pull out? Well, almost 3's. I can pull out one set of 3, but it still leaves me 1 3 inside because there were 4 of them. So the 3 came out as one set, but 1 stays inside. Is there a set of 3 x's? No, it's staying inside, and don't forget I have to keep that index on there. Now what's super nice is I notice after my simplifying is done that I have the exact same radicand with the exact same root index there. That means I'm allowed to join the outside values if they join. And 2y minus 3y do join. I get negative 1y or negative y, and I need to keep that last name hooked on, or that radicand right there, the cubed root of 3x. All right, we're ready for page 3. All right, last page actually for the notes here today. The definition of a to the m over n power, okay? These are what we call rational exponents, okay? So when we talk rational, we're talking rational exponents. Do you remember my definition of rational the other day? Anything that can be written as a fraction, okay? So to be honest, all those other ones we've looked at, they're really rational because we could have written them with over 1. We could have turned them into a fraction. But we're actually going to work with fractions now that can't be reduced, and how do they look as a power to a base, okay? So a couple of things. I think this is the easiest way to look at it. when you have a value, that's your base, and you have this fractional power, okay? The part on the top will be the power. That's going to make things get bigger. And the number on the bottom is the root, okay? So just a quick reminder, we can have the cubed root of something, I'll call it x, or we could write x to the 1/3 power, okay? Because the power is 1, we didn't increase it, but the root was 3, okay? So that's what this fractional or rational exponent is doing. The power's on top and the root's on the bottom. So we have two options. We can, in here, we could do a to the m, okay? No, they did root first, the root, and then they did m as the power. And I'm going to tell you that's the best way to do it. Or we could do the power inside and the root of both of them, okay? But I'm going to tell you first, especially because when I say no calculator on the quiz, next test and such, which hint, hint, I am saying that. So that's a heads up for those of you that are watching and hearing. Take the root first, then the power. Okay, you want to make numbers smaller, as small as you can first before you make them bigger. If you make them so big, your mind is struggling to wrap its head around what you're trying, those numbers are, and you probably can't do them mentally. And when I don't let you use a calculator, you could sit there all day trying to go down. So go down first to the smallest value, then go back up to the power. Okay, and a quick reminder, and I think it's funny that this is the one and only time in the notes they throw this out there, but a quick reminder of a negative power, okay? A negative power does not make a negative value. A negative power is a location change, and that's all. So if you have a negative power, this base, which was a whole number, will now go into the denominator, and I get it over 1, and now that power is positive, and it goes from there. So this is saying even if, no matter what kind of, whatever your exponent is over here, if there's a negative, it's going to change its location. By the way, if I happen to have 1 over a to the negative m, now that's going to move it to the top over 1, and of course you wouldn't have to put that 1 there, okay? So a negative power simply changes its location from numerator to denominator, and that is all it does. It does not make the entire thing negative. Okay. I feel like calling somebody out right now, but I'm going to be really nice, okay? I'm glad she's in my class, so I'm not going to call her out. All right, we're just going to simplify. We're going to practice all of our rules and make sure these are making sense. Okay, I know this first one looks a little bit easy, and I'm going to kind of overwrite it just to make sure this is making sense. So I have 196 to the 1/2 power. That means this 2 down here is my root, so it's the square root of 196 all to the first power, okay? Again, do I need to write that little 2 index? No, because it's implied you have the square root. But just remember, that's how that rational exponent changes or splits up. The bottom number is the root, the top power is the power. What is the square root of 196? 14. 14 to the first power, obviously just 14. So writing it as a square root is the same thing as writing to the 1/2 power. Okay, so on number 18, 8 to the 2/3. Remember, inside we're going to put the root first and the power second. And it's easier to start inside and make things smaller and then make them larger at the end. So let's do the root first. What number times itself 3 times is 8? That would be 2. And now we do 2 squared, and we get 4. Okay. All right. Again, I see this negative power. I'm not going to worry about it, and it does not make my answer negative. Okay. So I'm going to do 32, and I see the bottom number is my root, so that's the 5th root, and I'm going to leave this negative with the 4 on the power. Okay. I'm going to deal with it. I'm just not going to deal with it quite yet. What is the 5th root of 32? What times itself 5 times is 32? That would be 2. Now I'm going to take 2 to the negative 4th power. Remember, this is not a negative. It simply is going to put my 2 in the bottom. Okay, that's what that does. And what is 2 to the 4th power? 2 times 2 is 4, times 2 is 8, times 2 is 16, and I end up with a fraction for my answer. All right, 20 is looking big and scary. Stop and follow your rules, okay? My rule says that if I have a fraction, I'm allowed to reduce it first. Well, let's start with just these constants out front, the coefficients. 72 divided by 9, that's 8. When I have a value to the same base, x and x there, I have a rule that says we subtract their powers, 3/4 minus 1/3. Remember, the order on that is super important. You've got to do the top one minus the bottom one, okay? Guys, it's fractions. We need the same denominator to be able to subtract them. So I'm going to multiply by 3, I'm going to multiply by 4, I'm going to get 9 over 12 minus 4 over 12, because you can't read my writing. Wow. And that, I believe, makes 5 over 12. Okay, so I get 8 and x to the 5/12 power. Now, a quick reminder, variables to a fractional power, you're not doing anything with those. You can't take a root and all that good stuff. We're just going to leave it. That's its simplified answer, okay? We're going to leave it right there. All right, 21. I have the, all in this parentheses, 125, x to the 9th, y to the 6th to the 1/3 power. Remember, 1/3 power means it's the cubed root. So I can rewrite this whole expression, all of these inside because of that parenthesis, to the 3rd power. I'm sorry, 3rd root. What number times itself 3 times is 125, or what factor of 125 times itself 3 times is there in 25? 5 times 5 times 5 is 125, so I get 5. X to the 9th, and it's the 1/3 power. That means how many groups of 3 x's can I find in 9 x's? Well, I can find 3 groups of x's. Are there any left over? No, I'm done with the x's. When I get to y to the 6th, and it's the cubed root, I'm asking myself, how many groups of 3 y's can I find in there? Well, there's 2 groups of 3 y's, so I get y squared on the outside. Are there any y's left over? Nope. That's my answer. Okay. Side note, that is one way to look at this and get the answer. I want to give you another one if this one actually is easier for you to look at and think the same way. When you have a power outside of a parentheses, you need to remember it's like the distributive property. It goes to every value and every different term. It's not a term. That's what I need to be careful there. Like every part of this one term, okay? So that's really saying I'm taking 125 to the 1/3 power. I'm taking x to the 9th to the 1/3 power. I'm taking y to the 6th to the 1/3 power, okay? Well, the 3rd root of 125 we already know is 5. Notice here when I do 9 times 1/3, I get 3, which is the same thing I got up here. Y to the 6th to the 3rd, you multiply those together, 6 times 1/3 is 2, so I get y squared. So that's another way to look at those variables if that's easier than thinking I need a group of 3's. How many groups of 3's? When you see it there in the algebra, you see also where I get the 9 times the 1/3 is 3 and the 6 times the 1/3 is 2. So we get the same answer. It's just another way of looking at it. All right, we are on our last 2 here. 2, y to the 1/5 to the 4th power over y and to the 3/10 power. Only that 4th power only goes to the numerator because of the parentheses. It does not go to the denominator. So everything in top there has to go to the 4th power. So I have 2 to the 4th power and y to the 1/5 to the 4th power all over y to the 3/10. Okay. Guys, as long as you can, please take numbers to the power they are. If it's like 17 to the 4th power, don't do it. You're not going to do that without a calculator. But 2 to the 4th power, you can handle that. 2 times 2 is 4, times 2 is 8, times 2 is 16. Go ahead and give me that number. Remember, power to a power, we just multiply those two numbers together, so I get y to the 4/5. And it's over y to the 3/10. And we need to use the rule now because I see a y in the numerator and a y in the denominator. They share the same base, which means I can combine them into one value using my rule. 16 is not going anywhere. I get y to the 4/5 minus the 3/10 because of my division there. And I can change 4/5 to tenths, which is 8/10, and I get 16 and y to the 5/10, which is interesting because that's the same thing as 1/2. So two options here. You can write 16 and y to the 1/2, or you can write 16 and the square root of y. Either way you want to write it, I will take it. This is your choice. The reason I want to make sure you know to read it both ways is, once again, if you look for an answer in the back of the book, you may not see it the way you wrote it, but no, it can be written either way, and there's no wrong way there to write it. Okay, this next one, the 9th root of x to the 6th y to the 3rd. How many groups of 9 x's are there? There's not. How many groups of 9 y's are there? There's not. You would say I'm all done. But let's write this a different way. How about if I write it x to the 6th, y to the 3rd, to the 1/9 power, okay? Or the 9th root, right? Now, if I distribute this through, I get x to the 6th to the 1/9 and y to the 3rd to the 1/9. And I can think about doing a little, it's fraction work, reducing. Divide them both by 3, I get 2/3. So I get x to the 2/3. And then over here, I can divide them both by 3, I get 1 3, so I get y to the 1/3. This is a simplified answer. Or, because both of them are to the same root, I could put them back underneath the 3rd root and write x to the 2nd, y to the 1st, or just y. Okay? Now, when you look back to the original problem, could you have done that without all these writing it in different ways? If you think of your powers and roots as fractions, and they always need to be in simplest terms and reduced, yes. You could have looked up here at the top and said, look, all 3 of those net values can be divided by 3. Can I divide them all by 3? Yes, you can. And you would have got exactly what we just got on the last answer there. Okay? How are we feeling on it? I had your homework hidden here on the bottom. Practicing, page 43. Okay, there's a lot of them starting on page 43 and going from there, 3 through 114 by 3s, or all odds, whatever you want to do to practice, okay? I'm going to have an additional practice for you this week. Look for it on your Google Classroom. Try that as well. If you have questions, let me know.